Hi all, I'm Yaniv, CPO at Seemeore Data, a data efficiency platform over Snowflake. At Seemeore, we look at your workloads and Snowflake environment and try to optimize for performance and cost based on your company's SLO. As part of this effort, we develop various algorithms to understand how, what, and when to move things. In today's webinar, we will cover some core algorithmic logic that we've developed in Seemeore. Specifically, we will focus on the two which have the largest impact on your warehouse performance and spend. We'll start with how to determine the right warehouse size, when to scale up or down, and then dive into how to choose between Snowflake's Gen 1 and Gen 2 warehouses. By the end, you'll have a clear view of the logic behind these optimizations and how you can apply them to real customer environments. All right, let's jump in. Snowflake, as you probably know, is a cloud environment. And when you start working with Snowflake, it's very flexible. The storage costs are almost nothing. There's a lot of flexibility in how you can play with the processing power, with memory, and all sorts of things like that, meaning I have a lot of options I can play with, like concurrency and the amount of processing power I can allocate to each query, a lot of parameters. And when prospects come to us, at least for a significant portion of them, the decision about right-sizing the warehouse is more or less trial and error. It's arbitrary at first based on some rough calculations of the certain number of queries, how heavy they are in terms of resources. So then they set up some default size, see if it behaves well or not compared to expectations. And then I increase or decrease it, which is a good starting point, I guess. Now the question becomes, how do I allocate resources to my workloads in a smarter way and why? I'll tell you how we do it at Seemeore Data, the logic behind our resizing algorithm. So it all starts at a given state. And the big picture is pretty simple. We look at the queries running against a warehouse at a certain period in time, and then we try to rebuild that state from scratch under all sorts of different resource configurations. We look at every query, try to understand how it behaves today under the current configurations and why, and then try to predict how it will behave when different resource configurations are provided. Everything starts with the query. So it's common to think, or like it's just natural to think that when we look at a query, it behaves like this, like in a one scenario one, meaning the more resources I give it, the more it will cost me to run, but it will also run faster. And when I look at right sizing the warehouse, that's the behavior I use in order to optimize the size and configurations. The reality is different, significantly different. In fact, there are queries that behave like the one shown in number 1, but in reality, most queries behave like 2, 3, 4, or more precisely. A single query might behave like 1, 2, 3, or 4 in different places and different configuration settings, depending on its current settings. That is in relation to the resources you've given it. I'll give you an example. A very heavy query running on a very small warehouse that doesn't have many resources. Not only will it run very slowly, it will also cost significantly more than if you had given it more resources, okay? In other words, it will behave like number 4, and the more resources you will give it, it will eventually behave like number 3 until it moves to behave like number 1, and maybe if you just give it enough resources, it will behave like number 2. In the end, we'll see an example of a single query behaving like 2, 3, and 4 under different configurations. So queries behave this way or they don't behave this way. And we want to understand why, when, and how, or where we are at any given moment. So what we did and are still doing in all the algorithms we're developing is look at what data is available to us in Snowflake. And after that, we try to understand there's a lot of data. Some of it is more valuable, some less so. And we try to figure out what kind of correlation can we make between the data we extract from Snowflake about the query itself and how it affects things. So regarding vertical scaling, we have these 5 data points that we extract from Snowflake. And for us, these are the only 5 data points that really matter. These are the ones relevant for determining how many resources need to be allocated to the query. So warehouse size obviously is the amount of resources we allocate to the query. Query load percent is how much the query is parallelized within the warehouse. Byte scanned is probably the most important metric, but also the hardest one to use. We ultimately use bytes scanned to create some sort of mapping between the bytes scanned and how it will eventually translate to memory usage within Snowflake. That is to RAM, SSD, and HDD. In other words, how this mapping is done. This mapping is far from trivial, and it's never a one-to-one relationship, nor can it ever be completely precise. In any case, it's a very important metric, and it's probably the most significant factor affecting the runtime of that query. And the reason is that it affects the spillage. Spillage, if exists, is the main factor that impacts the query's runtime. Okay? Query duration is basically how much we're going to pay in the end. So as I said, each of these metrics affects some factor that influences the query's runtime. And in the end, we're paying for the query's runtime. Not exactly, but roughly. And it affects each of these, meaning the query load percent, whether it is 100% or 50%, will ultimately impact queue resources available bytes scanned. I map that to spillage and therefore time. And time is what I'm going to pay for. Makes sense, right? Okay. All right. So I assume you're familiar with this diagram. This is the Snowflake warehouse. We have the processing nodes, 8 on each warehouse node. We have the in-memory, the RAM, SSD, and so on, according to internet data, not the official Snowflake data. If we're talking about extra small, it's about 16 gigabytes, meaning each node has 8 gigabytes, and there are 2 nodes in extra small. So 16 gigabytes RAM, about 100 gigabytes of SSD, and then it doubles every time you go up a size. Basically, what we're actually doing is that each one of the data points we talked about so far is actually mapped in the warehouse in order to understand how it affects the runtime. So query load percent is here between the processing nodes. Byte scan is mapped within this whole context of RAM, SSD, HDD, basically spillage over time, and so on. I can see all of these things at the query level and some also at the node level within a query, and that's really important because when we look at the query profile, the nodes are ultimately what give us that extra level of precision. For example, if I spend 50% of my time inside some sort operation, which I can map out like this, then only 50% of the time do I need to apply the factor, which in the end I multiply by the time, the gigabytes, and so on. In other words, it's not enough to look only at the type of query. I really need to look at the node level. Most of the time we have enough information, and then I can do the mapping. Now, what I'm going to show now is dumbed down version of the kind of mapping that we did. It's not exact, but it's good enough. So really high level, as I mentioned, if we take query types, and it's not completely accurate, but it's accurate enough, except for some edge cases, and the bytes scanned, we will want to map the bytes scanned into memory. What we will do is that we will take a certain percentage based on the node's distribution that contains the relevant operation and map it out to memory usage with a simple multiple metric called RAM pressure. RAM pressure helps me find the effective gigabytes that will be in memory. And since I know exactly how much memory I have in RAM and SSD, then I'll be able to know exactly how much memory is going to spill over into local, remote, etc. Now, why is this important? As you've probably experienced or are experiencing in Snowflake, the speed ratio between the different memory tiers is significant, meaning orders of magnitude, like moving from cache to RAM to SSD is like moving from minutes to hours to days. So each level is an order of magnitude. That means if I didn't write the query correctly, and for one reason or another, it now spills to local disk. I've effectively tripled the query's overall runtime, causing a considerable performance impact. So spilling is generally bad because it increases our query time, but it's not always really bad since sometimes you just can't avoid it. I mean, sometimes it's part of the query plan because some operations require storage. And depending on the amount of data calculated, sometimes it just makes sense to spill when looking at the performance/cost ratio, meaning increasing the warehouse size doesn't necessarily give me the effective performance I want relative to the cost. By the way, you also won't always get better performance just by increasing the warehouse size. That means our optimization shouldn't be to completely eliminate spilling, but rather to reduce it as much as possible. So just to quickly go over the logic of what we're going to do, we take the query, we look at the data, and we try to figure out where the challenges of the query are. After we figure out where the challenges of the query are, we check how the query is structured, meaning the important nodes within the query, and we do the mapping to the various different levels of storage. And then subsequently, we determine the new estimated runtime of the query. There's another piece of data here that I won't get into right now, which is very significant in the end when it comes to determining the final price. And that's the change in the query's start time, meaning when the query actually begins, it's an endless story, very complicated. All right, that's it. So we calculate the new runtime of the query, okay? I mentioned to you earlier about the queries, right? And how they can be in different behavior places given different resources. So there's this one query we ran really big. I don't remember exactly how big, but very big. And we tested it on all sorts of different warehouses. Now, this query basically had a ton of spillage. You can see that when spillage was remote, the price performance behaved in a certain way when given more resources, meaning I could increase size and get better performance and lower cost. At a certain point, it shifted into this kind of catatonic state where I could scale up, get better performance, stay at the same price, and eventually it reached its limit, its plateau. All right. So all of this in the end comes down to the different ways memory is used. Okay, good. Gen 1, Gen 2. So Gen 1, Gen 2, logic is significantly simpler, more or less. Okay, let's go. Okay, so the improvements in Gen 1 and Gen 2, or rather the improvements of Gen 2 over Gen 1, are mainly here at the top part. We have stronger processing power. We have more cache, meaning we've doubled the amount of cache. And the I/O, meaning the RAM I/O, is significantly faster here. There aren't really any changes at the lower levels. What this means for us is that there are types of queries that are clearly going to be faster. Okay, so I'll start over. All the queries will be faster. The question is it worth it from a cost performance perspective? Meaning, will they be both faster and cheaper? Okay, so we have queries. We know what are the extra resources we provided them in moving to Gen 2. So there are queries that clearly, without a doubt, are going to be worth it. These are the processing heavy queries. On the other hand, there are also queries that clearly won't be worth it. These are the memory heavy queries, and there are queries that are in the middle, the ones that in some cases make sense from a cost performance perspective, and in other times they do not. The ones in the middle mess everything up because the first and second types are fine. I know what to do with them. So the queries in the middle are the complex ones where I need the logic to understand what they're doing. So just like before, here's the table. I'm not going to go over it. I made it so you could take a picture. What we did here is kind of a high level mapping, really high level, that shows which queries are definitely fine, which queries are definitely not fine, and which queries are in the middle. So what do we do here? The queries that are processing heavy will benefit from moving to Gen 2, so they are a definite yes. The queries that are storage heavy will not benefit from moving to Gen 2, so they are a definite no. For the ones in the middle, we need to build some king of metric, some ratio. All of these queries are queries that could potentially use only RAM for their storage, but under some circumstances also use the SSD, meaning there's some kind of ratio between the processing done in memory and the processing done in local disk I/O that above it makes sense to be in Gen 2 from a cost performance perspective, and below it does not. And there are a lot of edge cases for it, but this ratio is basically what ultimately determines for us whether this table is worth moving to Gen 2 or not. Now, as you all know, queries are the foundation, but queries on their own don't mean much in a single context. That is, queries come together with other queries and they affect each other because one query takes up resources and so on. At the end of the day, we're not paying for a query, we're paying for the warehouse's uptime. And a warehouse looks like this. It has all sorts of distributions of runtimes, all the data I mentioned earlier, the load percent, the spillages, and so on. There are a lot of queries. How many are there here? A lot. Over 150,000. So a single query doesn't really help us, but it's the basic unit. What we're really paying for is for the warehouse being up. So we take each query and essentially recalculate the precise runtime under all sorts of diverse resource constraints for each and every query, just like we showed here before. And then subsequently, we carefully rebuild the entire warehouse uptime, the warehouse run, based on the new query run times and new query begin times. We're essentially reconstructing all the intricate workloads, the complete runs of all these various workloads together under the newly defined and specific constraints. And then we can determine whether in the end it's worth moving the entire warehouse, not just a single query, for a certain period of time to different configuration settings. For example, I go from medium to extra large at 2 o'clock and to Gen 2 at 3 o'clock. We can set this not for a single query, but for the warehouse uptime. There are all sorts of edge cases that kind of mess up the whole thing, but basically the division, whether by time segments, warehouse runs, warehouse uptime, whatever gets recalculated under the new configurations. And we do this for every warehouse run under all the different configurations of each warehouse. That is for all the available options. And in the end, we suggest the optimal one. So everything I said here, basically, that's the high level logic for these algorithms, okay? If you dedicate enough time to it and use this logic, you can get to something pretty good. Thank you all for attending. I am happy to answer some questions, or if you want, feel free to connect with me directly. Thank you.